In astronomy, we use electromagnetic spectrum to observe the sky, starting with long wavelength, radio wave, infrared, visible light, which we could see, ultraviolet, X-rays, and finally gamma rays. But for this video, we will focus on ultraviolet, also known as UV.
Hi, I'm Paul, and I'm going to be narrating this presentation.
Hi, I'm Peter. I'm also going to assist with the narration.
So, UV is outside of the human visual capabilities. Our vision works from 400 to 750 nanometers, while UV spans from 10 to 400 nanometers. The higher frequency means more cycles per second, which means shorter wavelength, and also indicates higher energy. From left to right, the wavelength decreases while the frequency increases. So everything we see is in that little slice in the middle. It's pretty easy to tell that we're missing out on a lot of what's out there. So obviously the closest celestial source of UV radiation is the sun. All stars give out UV radiation, but the one we know most about is the sun, since it's the closest. The hotter a star is, the more UV radiation it will emit, and this is because higher temperature means higher energy, and UV light has more energy than visible light. The electromagnetic spectrum is typically divided up into three subspectra. The shortwave, which is 100 to 280 nanometers, the medium wave, or ultraviolet B, which is 280 to 315, and ultraviolet A, which is long wave, and it's 300 to 400 nanometers. The objects that we typically use UV light to study are the things that emit the most UV light, and those are very young, hot, bright stars, which have a lot of energy and therefore give off a lot of energetic light, which is where UV is, and also very old stars and galaxies. And also when studying galaxies, you can kind of help determine the age of it by seeing how many bright UV emitting objects there are within it.
Example of what we could see with UV is the Andromeda galaxy M31. Here's a clip from YouTube that explains more in detail about what we could see with UV.
This is M31, the nearest large spiral galaxy to our own. It's about 2.5 million light years away and more than 220,000 light years across. This is how we're used to seeing it in the visible light captured by ground-based telescopes. But visible light never tells the whole story. So between May and July 2008, Swift's ultraviolet optical telescope captured 330 images of M31 in 3 ultraviolet wavelengths. The total exposure time, 24 hours. We combine these images into this mosaic. It's the most detailed view of M31 in the ultraviolet to date. The first thing you notice is the striking difference between the galaxy's central bulge and its spiral arms. The bulge is smoother and redder because it's full of older and cooler stars. Very few new stars form here, because most of the materials needed to make them have been depleted. In contrast, M31's spiral arms sparkle with dense clusters of hot young blue stars. As in our own galaxy, the disk and spiral arms contain most of the gas and dust needed to produce new generations of stars.
And what we wouldn't be able to see if we didn't have UV would be elements of galaxies that would otherwise be obscured by clouds of gas and dust. Since most of the UV radiation that hits our atmosphere is absorbed before it gets to the ground, most UV telescopes are in space. And another reason that they're in space is that there's a lot of UV light pollution from people, mostly drug smokers, who use black lights to make things look more interesting. And since we cannot see this light, we must use detectors that are sensitive to the light, which store the data, which can then be processed for human viewing. Here is a simple diagram of a telescope with UV capabilities. This is a Hubble telescope, and it's a Cassegrain style with a big mirror in the back, a smaller mirror up towards the front, and the instrument array at the focal point in the back. So UV detection, there's a lot of different ways to do it, and some detectors have a wide frequency spectrum that they can detect, and it overlaps the kind of arbitrary categories that we've made. So some may detect all the way down to UV, up even through infrared. And one of the original instruments on the Hubble telescope was the faint object spectrograph, which could see from 115 to 850 nanometers, which covers most of UV and the entire visible spectrum. And these general modules tend to be replaced with ones that have more specialized or multiple specialized arrays, such as the Space Telescope Imaging Spectrograph, which had 3 different UV imaging arrays, which each had a narrow frequency response. So since we can't see this light, and the telescope gathered it and stored it, we have to translate it into a format we can see. One easy way to imagine this is to imagine adding 350 nanometers to every wavelength captured. So far UV data would be like in the blues, towards the high end of what we can see, and near UV data would be up towards the reds, which is at the lower end of what we can see. This is kind of pretty good because the ranges are fairly similar, like the amount of wavelengths in UV and visible. Another way to do it is, it's easy to imagine in digital image processing, is to assign the low end of the image a digital value of 0, and the high end the maximum value. So if you're dealing with an 8-bit image, it would be 255. So like 10 nanometer light would be black, and 400 nanometer light would be white. And once you do this, you can add false coloring to it. So you could say 10 to 100 will be reddish colors, 100 to 300 will be bluish, 300 to 400 will be greenish. And this can be arbitrary, so you can add any kind of coloring you want to highlight certain features. You can also use something called lookup tables, which basically just maps one color value to another. Here's a little image comparison of a UV image of a galaxy versus a visible image of the same galaxy. And you can see that there's a lot of dust in the visible one and more detail, even though it seems to be at a lower resolution in the ultraviolet one. So we can see a lot of things even in our own sun, which is something we see every day. Features that are either washed out or just invisible in visible light can be seen using UV light.
This is a list of links that we use as sources. Thank you so much, and I hope you enjoyed this presentation.